In this lesson, we will discuss continuity and derivatives of complex functions. We'll begin with the definition of a complex function being continuous at a point. Let f map complex numbers to the complex numbers. Say that f is continuous at z0 if the limit of f of z as z approaches z0 equals f of z0. So we note that this definition implies that the limit of f of z as z approaches z0 exists, and that f of z0 exists, that is, f is defined at z0, and that these two numbers must be equal. Now we'll give a precise epsilon delta definition of continuity. We'll say that f is continuous at z0 if for every positive number epsilon there exists a positive number delta such that the distance from f of z to f of z0 will be less than epsilon whenever the distance from z to z0 is less than delta. So the idea is that as z approaches z0, the values of f of z are getting closer and closer to f of z0. We say that f is continuous on a set S if and only if f is continuous at every element z in the set S. Now, continuity of complex functions is formally the same as that of real functions, so we have all of the usual theorems about continuous functions following for complex functions. We have the following theorem. Suppose f and g are continuous at z0 then the following functions are continuous at z0. The sum of f and g, so the function f plus g, the difference f minus g, the product function f times g, the quotient f divided by g, provided that g of z0 does not equal 0, and the composition f composed with g, provided that f is continuous in a neighborhood of g of z0. So these proofs are essentially the same as the proofs for real-valued functions, so I'm going to omit the proof of this theorem. Next, we'll prove a theorem about continuous functions that are non-zero. Suppose f is continuous and non-zero at f of z. Then we can conclude that f does not equal 0 in a neighborhood surrounding z0. So f of z does not equal 0 throughout some neighborhood of z0. So for the proof, I'm going to suppose that f of z0 is not equal to 0, and that f is continuous at z0. And I'm going to choose my epsilon to be equal to the absolute value of f of z0 divided by 2, which is positive, since f of z0 is not equal to 0. So by the continuity of f, we can find a delta. So then there exists a positive number delta such that the distance from f of z to f of z0 is less than epsilon, which is f of z0 an absolute value divided by 2. Whenever z is within distance delta of z0. Now, we're trying to show that f of z can't equal 0 in this delta ball around z0. So for a contradiction, let's suppose that f of z equals 0 at some value z1. So let's suppose f of z1 equals 0, but where z1 is within a delta ball around z0. Then the absolute value of f of z0, which is not equal to 0, can be rewritten as 0 minus f of z0 in absolute value. And that equals the distance from f of z1 to f of z0. And since z1 is within distance delta of z0, we know that this value will be less than epsilon, which equals absolute value of f of z0 over 2. So at the beginning of this statement, we have f of z0 an absolute value, and now we show that that is less than the absolute value of f of z0 divided by 2, which is impossible. So this is a contradiction. And this concludes this theorem because we've shown that f cannot equal 0 in this delta neighborhood around z0. So this theorem proves that if f is continuous and non-zero at a point, then it's non-zero in a neighborhood surrounding z0. Recall that we proved the fact that the real part of z will, in absolute value, will always be less than or equal to the absolute value of z, and similarly for the absolute value of the imaginary part of z for any complex number z. So this fact can be used to prove the following theorem. So I'm going to omit the proof. If the function f of z is written as u of z plus I v of z, where u of z and v of z are the real and imaginary parts of f, then this function is continuous at z0 if and only if its real part u of z and imaginary part v of z are continuous at z0 as well. So we'll be using this fact in the future, and the proof is pretty straightforward once you use the fact that the real part in absolute value is less than or equal to absolute value of z for any complex number z, and the similar statement for the imaginary part of z. We see that a complex function is continuous at a point if and only if its real part and imaginary parts are continuous at that point as well. One last theorem on continuity. Suppose f is continuous on a closed bounded region R. Recall that a region is bounded if it lies within some circle centered at the origin. Then we can conclude that the absolute value of f of z, this function, attains a maximum value somewhere on the region R. So to restate this, that is that there is a value m, a real value m, such that the absolute value of f of z will be less than or equal to m for all z in the region R, and at least some value z0, f of z0 will actually equal m. So equality holds for at least one point z0 in R. So this statement is analogous to the extreme value theorem for continuous real valued functions, and in fact the proof of this theorem just follows from that fact, because absolute value of f of z is a real valued function. So for the proof, we see that the absolute value of f of z is equal to the square root of the sum u squared plus v squared. From the previous theorem, we know that u and v are continuous on the region R, since the function f is continuous on the region R. So this expression, square root of u squared plus v squared, will be a continuous real valued function on a closed bounded region R. So then it follows from the extreme value theorem in calculus So by the extreme value theorem for continuous real valued functions, which states that a continuous real valued function defined on a closed interval will attain its maximum somewhere in that interval. So by the same proof, we can show that f of z, an absolute value, reaches an absolute maximum capital M somewhere in R. So in fact, later we'll show that the maximum occurs on the boundary of R. Next, we'll discuss derivatives of complex functions. Let's begin with our definition of a derivative. So let f be defined in a neighborhood of z0 then the derivative of f at z0, we use the same notation for real valued functions, denoted by f prime of z0, is defined as the following limit. The limit z approaches z0 of the difference quotient f of z minus f of z0 divided by z minus z0, provided this limit exists. So this limit definition of a derivative is the same as that of a real valued function. If f prime of z0 exists, we say f is differentiable at z0. And we have alternate ways to write this limit by making the substitution delta z equal to z minus z0 where delta z can also be written as delta x plus I delta y. Then we can write delta w equal to f of z0 plus delta z minus f of z0 and f prime of z0 can be written as the limit as delta z goes to 0 of delta w over delta z. And in Leibniz notation, we can write this as dw dz, the derivative of w with respect to z. So with this limit definition of derivatives and our limit laws that we've already shown hold for complex functions, we could find derivatives of complex functions just like we did in calculus. So for example, let's take the derivative of the function f of z equal to z cubed. And for any complex number z0, f is continuous at z0, and we can define the derivative at z0 to be equal to the limit z approaches z0 of f of z minus f of z0 over z minus z0. Using the definition of f, this equals the limit as z approaches z0 of z cubed minus z0 cubed over z minus z0. And to divide with this limit, I'm going to factor z cubed minus z0 cubed, as the limit as z approaches z0 of z minus z0 times z squared plus z times z0 plus z0 squared divided by z minus z0. So I can cancel the common factor in the numerator and denominator z minus z0, and I'm left with a polynomial, and this will be equal to the limit as z approaches z0 of z squared plus z times z0 plus z0 squared. And since this is a polynomial in z, I can just plug in z0 for z and obtain z0 squared plus z0 times z0 plus z0 squared, which equals 3 z0 squared. So the derivative of f at z0 is 3 z0 squared. For our next example, let's look at the function f of z equal to the absolute value of z squared. We'll actually show that this function is differentiable only at z equals 0. So let's take the derivative of f at z0, and this is equal to the limit of, as delta z goes to 0, of f of z0 plus delta 0 minus f of z0 all over delta z. And using the definition of f, this equals the limit as delta z goes to 0 of the absolute value of z0 plus delta z quantity squared minus the absolute value of z0 squared all over delta z. I'm going to write this limit using the fact that the absolute value of z squared equals z times z bar, and we'll write this numerator as z0 plus delta z times z0 bar plus delta z bar, and absolute value of z0 squared is z0 times z0 bar. This is all divided by delta z. And when I multiply out the terms z0 plus delta z times z0 bar plus delta z bar and simplify, I will get the limit as delta z goes to 0 times the fraction z0 delta z bar plus z0 bar delta z plus delta z bar all over delta z. And break this up into 3 fractions, I get the limit delta z goes to 0 of z0 delta z bar over delta z plus z0 bar plus delta z bar. So if the function is differentiable at z0, this limit will exist. So then as delta z approaches 0 from any direction, this limit must be unique. So if we look at z0 approaching 0 along the x-axis, then delta z, which is delta x plus I delta y, the delta y will be 0 along the x-axis, and delta z bar will equal delta x minus I0, because again delta y will be 0. So we see that delta z will equal delta z bar along the x-axis, and therefore the derivative at z0 will be equal to the limit as delta x goes to 0 of z0 plus z0 bar plus delta x, and as delta x goes to 0 we get z0 plus z0 bar. Now along the y-axis, delta z will equal 0 plus I delta y, and delta z bar will equal 0 minus I delta y. Therefore, f prime of z bar will equal the limit as delta y goes to 0. So delta z bar over delta z will equal negative 1 now. And so we get that this limit equals the limit as delta y goes to 0 of negative z0 plus z0 bar minus I delta y. And as delta y goes to 0, this equals negative z0 plus z0 bar. Now we'll use the fact that limits must be unique to conclude that the limit along the x-axis will equal the limit along the y-axis. So we get that z0 plus z0 bar, which is f prime of z0, must equal negative z0 plus z0 bar. But this implies that z0 plus z0 bar equals negative z0 plus z0 bar, which implies that z0 equals negative z0, and that implies that z0 equals 0. So the only way that this derivative at z0 can exist is if z0 equals 0. In which case the derivative of f at 0 equals 0 plus 0 bar, which is just 0. So you see that the function f of z equals absolute value of z squared is only differentiable at z equals 0. Notice that this function f of z equals absolute value of z squared is continuous on all of the complex numbers, but it's differentiable only at the number z equals 0. So we see that for a function to be differentiable, it is not enough to know that the function is continuous at z. But it is true that if a function is differentiable at a point, then it must be continuous at a point. If f is differentiable at z0, then f is continuous at z0. So to prove this theorem, suppose that f prime of z0 exists. then the limit z approaches z0 of the expression f of z minus f of z0 will have to be equal to 0 in order for f to be continuous at z0. By properties of limits, I can write this as the limit as z approaches z0 of the fraction f of z minus f of z0 over z minus z0 times the limit as z approaches z0 of z minus z0, since the product of the limits is the limit of the product. Now, as z approaches z0, the limit on the left equals f prime of z0, and the limit on the right equals 0, so this equals 0. Therefore, we can conclude that the limit as z approaches z0 of f of z equals f of z0, which is the definition of f being continuous at z0. So differentiability at a point implies continuity at the same point. Since the limit definition of complex functions mirrors the limit definition for real-valued functions, this means that all of the differentiation formulas from calculus will follow for complex functions. So when we're finding derivatives of expressions of functions, we can write d over dz of f of z or f prime of z. These all mean the derivative of f at the point z. So oftentimes we can just use the Leibniz notation d over dz to denote differentiation, or if we have a function form, we can write f prime of z, just like we did in calculus. So as I stated, all calculus differentiation rules follow for complex functions. So we can assume that we have all the same rules, like the sum rule, the difference rule, product rule, quotient rule, chain rule, and so on and so forth. So all these same derivatives that we did when the variable was x will follow for functions of a complex variable z. So an example of notation, so if I want to take the derivative with respect to z of the polynomial 3z squared minus iz plus 1 plus I. Just as in calculus, the derivative of a constant is 0. We have the power rule. In other words, the derivative of 3z squared will be 6z. The derivative of iz will be minus I, and the derivative of a constant 1 plus I will be 0. So you would just get 6z minus I. An example of the chain rule, the derivative with respect to z of 2z cubed plus I, the quantity to the fifth power. Well, the outside function would be the fifth power, so we have the derivative of the outside function, 5 times the quantity to the fourth. So there's the derivative of the outside function evaluated at the inside function, so 2z cubed plus I, times the derivative of the inside function, 2z cubed plus I. That's the chain rule. And so the derivative will equal 5 times 2z cubed plus I, quantity to the fourth, times 6z squared, which is the derivative of 2z cubed plus I. And this expression could be simplified to 30z squared times the quantity 2z cubed plus I to the fourth. Do an example of a derivative of a quotient. So the derivative of a quotient, high over low, is low d high minus high d low over the square of what's below. So low would be 2z minus 1. D high, the derivative of z plus 1 would be 1 minus high d low, so minus z plus 1, the quantity, times the derivative of the denominator, which is 2, over the square of what's below. So I'll just write 2z minus 1, the quantity squared. And this expression will simplify to minus 3 over 2z minus 1, the quantity squared. So I'm going to assume that all students in complex variables are familiar with the differentiation rules of calculus. And if you need to brush up, you can take a look at any calculus textbook to find the standard product quotient rule, chain rule, power rule, sum rule, difference rule, and so on for finding derivatives.